Welcome back to educator.com. We have another lesson today in intermediate C++. Today, we are going to do the first half of object-oriented programming. Okay, one of the strengths in C++ over its predecessor C is the ability to implement object-oriented programming, typically called OOP. You'll also hear OOD sometimes as object-oriented design, or OOA, object-oriented analysis. You have to do analysis and design before you do the programming usually, but that's okay. We're not going to talk about too much of that. So the data and the structures are gathered into an object. It's different from earlier ways of looking at things is how you organize your data. So you'll have an object that contains all your data and functions that operate on those data, and they're defined in classes, and they're isolated away from other objects. You have objects that are responsible for certain functions, have other objects that are responsible for doing other things. So the object-oriented programming emphasizes these important concepts. Now, earlier than that, you had to do things like this anyway to have a strong, easily maintained program, but object-oriented programming emphasizes it more, which we have data abstraction, encapsulation. Inheritance is completely new. It's done in object-oriented programming. You don't see that in functional programming at all, or procedural programming, excuse me. And of course, polymorphism, which is also important. But you do see a little bit of that in earlier programming styles. But object-oriented programming explicitly defines ways you can have polymorphic behavior. Now, your objects have different types of relationships. In particular, they have an is-a relationship, where an object is some other object, such as a horse is an animal, or a car is a vehicle, that sort of thing. And then you have has-a relationship, where a car has a tire, a car has a front seat for the passengers, a horse has a tail, etc., etc. Now, one of the things C++ has that other object-oriented languages don't have, it has multiple inheritance. So your object class can inherit from more than one class, and this thing wrapped weird. There should be a plus here, it should say C++, and that plus shouldn't be there. But we won't worry about that today. So an object can inherit. You have an object which is of this, is also is of that, and so if there's attributes, if there's functions and data that can be used in that parent or superclass, then you use that one. If it's something that's in this other one that's useful, then you use that one. Have as many of them as you need. So you can inherit more than one class. We're going to talk about construction today. A class object has to be constructed when you initialize a new one. There's also a destruction, but we'll talk about that in the next lesson. So we have construction, which allocates the memory that will hold the object instance, and it should be controlled by the programmer. If you don't provide a constructor, the compiler will give you one, because you need to have a way of constructing a new object. Now, the default constructor that the compiler gives you may not be what you need, so it's always a good idea. It's a good practice to make one, even if it doesn't do anything. Just put one there so you can add things to it later if you need to. Now, there's a deep copy versus shallow copy, which we'll talk about. If you need deep copy, you have to provide a copy constructor. So when you copy an object, this object into this other object, there's all the parts and members and pieces of it that have to be copied also. And the compiler does a shallow copy if you don't provide it a copy constructor. Sometimes you need a deep copy. Now, we will talk about that later in this class. Okay, historically, we've had some distinct ways of programming design. There's the procedural, where you have an algorithm, we do this step, and then we do this step, followed by this step. We make a test. If the test is true or false, then we'll wrap around, we'll go back and do this test again. That's been pretty much, you're still pretty much doing procedural programming, no matter what you're doing, except for some strange types of language we're not going to talk about at all. Some years ago, structured programming was defined. So instead of having a go-to here, we'll go-to back to there. And we have a go-to in here, which goes down to there, which cause all sorts of spaghetti coding problems where your code would go up and down and left and right. And it was very difficult trying to fix that when there was a bug in it or for someone to understand it. So structured programming introduced the concept of putting everything inside of a code block where you do not jump out of it and you do not jump into it. So you have a if statement. This is, instead of an if test where you jump around it, you have a block, an if test at the beginning of it. If it's true, we will handle this block. We'll have this block. This block of code needs to be executed some number of times, so we'll loop around in this block of code. Now, object-oriented, on top of having these blocks in structured programming, you also conglomerate all of your data and methods inside an object, because all the data here is associated with this thing. So we have some important concepts that are emphasized. Abstraction. The object is not a real object. It's an abstract representation of the object. It's the data that represents the real world object. The data that's important to us is kept in our object as an abstraction. Encapsulation. We only have the data that's related to that object. We don't keep data that's related to other objects in this object. So it has to be encapsulated in this object, and this other object can't get to it except in controlled access. Inheritance. We have a class here, such as we mentioned before, a vehicle. It has certain data, it has certain methods, there's things you can do to a vehicle data. And then we have an auto, which is a vehicle. And as a result, it inherits from the vehicle object certain attributes and certain methods and functions that, for example, a vehicle will have a speed. Well, because a vehicle has a speed, an auto has a speed. Now, they have to make some changes to that and how that speed is controlled. A vehicle can have a method that says accelerate. We want to increase the speed, or we want to decrease the speed by giving a negative acceleration. An auto may have methods that says brake. And what that brake will do is use the vehicle's accelerate but give it a negative number. We're going to slow down the speed of the auto vehicle. And then we have polymorphism, where you have multiple objects. They can all have the same method with the same name, but they operate on different objects. When they operate on different objects, they do different things. Like, for example, we can have another thing. Let's call this a plane, which is also a vehicle. But it works very much differently in a plane than what an auto does. For one thing, there is no brakes. Well, technically there are air brakes, but you don't have friction-type brakes in an airplane that you have in an auto. You have the brakes, the air brakes, where the flaps will come down to slow the airplane down. And so when you call brake in an airplane, as opposed to calling brake in an auto, it's the same function, it's the same name, but it has totally different meaning for a plane than it does for an auto. So, like I said, our data structures are gathered into an object. An object is defined in a class. Now, what a class is, sometimes you hear the words object and class used interchangeably. Technically, a class is the definition of the object. It says, okay, our class has got this data, this data, this data. It has this method that operates on that data. When we instantiate a new object, when you declare one like it's with a type, then the object will use that class as its definition of how its internal structures work. And we'll see some details how that works today. So we're looking at some terminology. Like I said, an object is a collection of related data. And like I said, you'll sometimes hear object and class used interchangeably, but technically when we're looking at an object, sometimes you'll use an object interchangeably with the instantiation of an object. So bear with me here. We have an object as a collection of related data and methods that represents something. So you have a vehicle, you have a horse, you have a bank transaction, whatever it is that you have, it's an object that's defined. And the object has fields, sometimes called attributes, sometimes called members or member data, which all pretty much is the same thing. It's the piece of data that defines some part of the object, its current state, its current size, its current weight, whatever it is, the name of the object. I love to have objects have names. You can call them all kinds of cute things. And so an object owns that data. And I don't care whether you want to call them fields, attributes, members, some languages will have properties, whatever. Basically, it's the data that's owned by the object. An object will also have methods or a member function. Those are specific custom-made functions that operate on that object data. So an object, that's where your class becomes important, because you build an object, you don't have to bring in a copy of the function each time. The function code will be in the class. So when you take an object and use one of that object's methods, you're calling the class method to operate on the object's data. So a class defines the attributes and the methods. So you can define all the objects as being part of that class. The class generally is what inherits from other classes. So inherit behaviors, the data, the methods, what have you, from a superclass. And subclasses is the other way, is they're derived from the class. So if we put a little diagram here with a vehicle there, an automobile there, and a race car here. So the auto is a vehicle. So the auto is derived from the vehicle. The vehicle is the superclass of the auto. And we'll go down one level further. A race car is an automobile. So the race car is derived from the automobile. The automobile is the superclass of the race car. Now finally, we have an instance, which is instantiation of the class. It's like declaring it as an object. Before we went into object-oriented, we would define an integer. And we would say int a and give it a value is 0. And what that does, that gets an a as an object. It's not really an object technically, but it is a variable. It holds a piece of data. It allocates enough bytes in memory to hold an integer and then initializes it to 0. You can also instantiate a auto. Let's give it its class name, auto. We've already used a, we'll call it A1. So now we've instantiated an auto, given it the name A1. The compiler will allocate enough memory to hold all of the data that's associated with the class auto. So this will actually have memory required to hold that particular data. Now we'll have an example. Let's have a horse. My favorite horse, Mr. Ed. If that reference is too old for you, just look it up. So we have a class horse. Now, the difference, there is a subtle difference between a class and a struct in C++. We could also have a struct and then let's call it H, since we've used, let's call it horse 1. The struct terminology is inherited from the C language. It's changed to a class in C++. The only difference in C++ is the default accessibility. A struct, just all the data is public by default. So if you want something to be private, you give it the private keyword. In a class, it defaults to private. So if you put your private data up front, you don't need to specify private. But here we're specifying because it's a good idea to specify it anyway. So here we're defining from this point forward, this data is private access. Only that object can access directly this data, which is the name. And here's our field or attribute, which we've given a type of string. The variable name is name. And following that, we have protected. Now, what protected means is that only the object can access it, but also if you have an inherited class, if you have a derived class rather, the derived class can also access the protected data. It'll be part of the object, and the protected data will be available. Now that may be a little confusing. Let's do a real quick example. If we have a vehicle, and it has private attribute of speed, and let's put PRV for private, and then we have a protected one. Let's do PRT for protected. And let's have it be its age. Now we inherit that class into an auto. And when you instantiate an auto class, the speed data is saved in the auto object. The age data is also saved in the auto object. So there is a speed and there is an age, but the auto object cannot change its speed. It can change its age. Actually, that probably should be the other way because the auto changes its speed all the time. Its age, once if it's 5 years old, it stays 5 years old until next year, right? But that's okay. These are just simple examples. Now, next we have public, and that's access that is available to all other objects. It's accessible to the inherited object. It's accessible to objects that are not related to it at all. It's accessible to the main routine. So here's our constructor. This is a default constructor, and it's a default constructor because there are no parameters. So we can instantiate this horse just by giving it its name. And now we've instantiated a horse which will have a name, and will have a speed, and it has the constructors and the methods that can operate on that object. And here's a destructor. Notice it's got the tilde. That makes it a destructor. One thing I should mention. Here's your class name, is horse. Here's your constructor name, is horse. The constructor name matches the class name, and there are no types associated with it. That's what makes it a constructor. What makes it a destructor is when you put the tilde in front of it. Now it's a destructor. So when that object is destroyed by any means available, and we'll talk about some of those means later, the destructor will be called. And then, well, why do we need a destructor? Well, it depends on what you do in the constructor. You might allocate some memory yourself. It says, okay, the horse has got a saddle, so we need to go buy the saddle, for example. We need to construct the saddle. So when we destruct the horse, the destructor needs to destruct the saddle. Now here's a quick method. Its type is void, so there's no return type. And it's gallop, and this is a member function. So we can call the gallop function, member function of the horse object. So here we have h1. We can say h1 dot gallop to call that member function. So now this horse is going to be galloping. So here we have an instance here, Mr. Ed. Here we have an array of instances, an array of 20 instances of horse. So we've got Winston Downs somewhere. We've got 20 horses in a line, and they're raring to go. All right, abstraction, very important concept in object-oriented programming. Abstraction defines the essential characteristics of an object or class of objects, particularly those that are needed for the application being programmed. There's lots and lots and lots of data that's associated with any object. You're not necessarily interested in all of them. If you have a banking routine, you're interested in the money aspects. You're not interested in the color. You're not interested in all the various other things that are associated with it. So the emphasis is on essential. Data for a horse could include its weight, its age. So if it's a racehorse, the weight and age have an effect. Its best race time, its most recent time. You could have an included object, your history of times that this horse has run at whichever races it's run at, etc. All that can be part of the horse object. The horse's astrological birth sign might be interesting, but unless this is a program that's dealing with astrology, it's probably unessential. It's a non-essential data for a racing program. So the classes are defined with those characteristics that distinguish one class from another. And where this gets important is things like, well, it has the same name, it has the same function, it looks the same, but it is different because it's in a different class, so it has to be treated differently. And for example, we have an employee. He has a name, he has a wage, etc. A company has a name also, and an annual profit, which is very similar to a wage, but the wage is not treated the same as an annual profit, especially if you're talking about tax laws. An employee is taxed at different rates for different reasons with different types of deductions than a company is. So although the data is similar, you might be tempted, well, we'll make it all the same object because they all have a name, they all have an income. Well, an employee's income is different from a company's income. So you distinguish that into two different objects. You abstract them into two different objects. And then we have encapsulation. We compartmentalize the data of the abstraction into the objects. So the data and methods govern the state of an object, what it's doing, where it is, how big it is, and that data is protected from unauthorized access. It's hidden away inside the object. So the big issue with object-oriented programming is divide into objects and assign those objects to different developers on your team. So this developer becomes the expert in this object. Another developer is not an expert in that object. He's an expert in some other object. So he doesn't know that certain data in this object should not be changed in certain ways. So this data is kept away from him. If he needs to change that data, a method will be provided for him to change the data in a controlled manner. So the private data cannot be viewed or changed by other objects because the other objects do not have a need to know. They are under the control of this object. The access is restricted. Now, public methods allow controlled access to the private data. So we say, here's some data. I'm going to set your name to something. So the input data can be validated. I'm going to set your age. So the validation might say, well, wait a minute, age cannot be a negative number. So if you try to give me a negative number for an age, I'll throw an exception. I'll throw your number right back at you. And output data can also be computed. So I need to find out what your age is. So I'm storing the age in the number of days that you've been alive. Well, I need the age in years. Okay, well, we'll just take the age. I'll just call a method that says get age in years. Get age in years looks at the private data. The other objects don't have to know how the data is stored internally. So I need your age in years. So I call a method, give me the age in years, and that method will say, I'll take my age in days because my object knows that it's age in days. I'll just divide it by 365. There you go, there's your age in years. Now, protected data, of course, are accepted, as we mentioned earlier, are accessible to inherited classes. So when you design your system and you design your classes, you make the decision which data should be protected so it'll be accessible to the classes that are derived. Now, sometimes you need to break some of the rules. So you have classes, methods, you flag them as a friend, and the friend class or function is given access to the private data. When you're writing an object, you're designing the code, you probably also want to be in charge of writing the friend classes. So when someone calls the friend, if you really need something that's not inside the object, that has access to the object's internal data, then you write a friend class or a friend object, and then other objects can call the friend to get inside information. And of course, inheritance. Without inheritance, you don't have object-oriented programming. You have a relationship between object classes where an object inherits data, attributes, methods, behaviors from the superclass. And it's usually called an is-a relationship. So an auto is a vehicle. A race car is an auto. A motorcycle is a vehicle. A dirt bike is a motorcycle. An SUV is an auto. A bus is a vehicle. A bus is not really an auto. It's up to your design team. You want to make an auto be a bus? You want to make bus be an auto? It depends on how you want to define what the methods are. What do you need to do with a bus? You might just want to say, well, a bus and an auto are the same thing as far as we're concerned. So you don't not even have a separate object for it. It's up to you for your design team and your application. So an object is a kind of some other object. It's some specialization of the object. And this facilitates code reuse to a certain amount because, okay, I have the auto object. I don't need to code up how to calculate its GPS position or what have you. That's already being done by my vehicle superclass. But what's more important is modularization. So we have the auto is separate from a motorcycle and those sorts of things. So keep things modular in pieces so that they can be divided into teams more easily, and pieces of it can be taken out and put in other applications as necessary. If you find bugs, you told the bugs, it's pretty sure it's in this object, and so we make changes to this object without affecting the other objects in the system. So we have some examples. Cars, ships, airplanes are kinds of vehicles. So you have a vehicle class, and then a car is a vehicle, a ship is a vehicle, an airplane is a vehicle. So the vehicle attributes could include its position. You've got your GPS device inside the vehicle. Where is it located? How fast is it going? Is it accelerating? How heavy is it? Et cetera, et cetera. Now, an auto is a vehicle. And in this particular example, big deal. It's just a vehicle. There's nothing else special that you want to add to it. A ship is a vehicle, but we need to add additional attributes. In particular, we need to know its buoyancy. You might have you get back to another design decision. Okay, we have a ship is a vehicle with buoyancy. How about a submarine? Is a submarine a ship that goes under the water? Or is it merely a ship with negative buoyancy? See, that's where you get your design decisions. You have to work which way is the better way to implement these things. And of course, an airplane is a vehicle with altitude. How high above the ground is the airplane at this particular time? Something an auto or ship will never need to worry about. And then we have polymorphism. It's the ability for the methods and functions to take on different behaviors depending on the object that the function is applied to. Now, you've seen operator overloading as a form of polymorphism. So this is not the minus sign. I'm going to erase it. That's just the bullet for the slide. So we have A plus B. We have a plus operator. Now, what does the plus operator do? Well, that depends on what A and B are. If A and B are integers, It says, okay, A is 7, B is 3, add them together, that's 10. If they're strings, A is equal to Alvin, and B is equal to Sylvain, then A plus B will concatenate the two strings together. Same operator, completely different functionality. So your parameter signature is another way, particularly with functions, to get polymorphism. We have the getLine function as an example, which takes a character string and an integer. That uses a different delimiter. The default delimiter is new line. So it will read the line, it will load this character string array until it gets to the new line, and it will stop. Now we have a slightly different signature here, a slightly different set of parameters. We have the buffer, we have the integer, and we have the character that we're going to stop at. We might want to stop at space, we might want to stop at a tab, whatever, etc. So it behaves slightly differently. Now methods are inherited from another object. They can be overwritten and customized to the new object. So we have your vehicle object, and it has a brake. That means slow down. Now what the brake does, depending on whether you have an airplane or ship or car, you'll call a different brake. So we have the vehicle. Let's say we have an auto, which inherits from the vehicle, and it overrides the brake function. And we'll have an airplane. Let's put that over here. And it also has a brake function, which also overrides the brake function of the vehicle. Now, as I mentioned earlier, the brakes on an airplane means lowering the flaps. The brakes on the auto means squeezing your brake pad or your brake drum on your tires and creating friction there to slow it down. So if you just have a vehicle and you have a function that operates on the vehicle and it needs to apply the brakes to the vehicle, that function doesn't need to know whether it's an airplane or an auto. It just calls the brake function of the vehicle. If that object is an auto, it calls the auto brake. If the object is an airplane, it calls the airplane's brakes. Now, ship, that's another completely different set of brakes. Let's put a ship here. Now we have a brake for that, and let's move this inheritance line way over there so we get right past it. Now, depending on the type of ship, you have a large ship. They actually got these very large cruise ships that have got the propellers on rotating pods. So when the ship is going this way, going forward, the pod is facing towards the rear. When they want to slow it down, the pod actually rotates until it's facing the other direction to slow the ship down. So that's a brake function, which works completely differently. Now, if you have a little sailboat, it's about 12 feet long, you don't got brakes. So now, talk about a little bit about object relationships. So let's consider two objects, a car and a vehicle, which we've been talking about ad nauseum here. A car inherits attributes and behaviors from the vehicle because it's a certain kind of vehicle. The car is a vehicle. But there's other types of relationships. Consider two other objects, a car and a tire. Now, a car isn't a tire isn't a car. But a car owns tires, it has tires. A car has a tire, it actually has 4 tires plus a spare tire usually. So we have ownership. So we have a motorcycle object. It is a vehicle, it has a tire, it has 2 tires. You have a unicycle, it has 1 tire. So the has-a relationship is also called composition because you have a bunch of objects together that compose and make up, they put together a object in their collection. A tire object by itself isn't much used except, of course, in a tire store. But a car can have a front seat object and a back seat object, and perhaps the back seat object is a seat and the front seat object is a seat, and it can have 4 tires and it can have headlights, all these other various objects that are put together to compose, to build the larger auto object. However you want to work it. So let's have a quick example of inheritance. We have a horse here. It has a private string name, a protected speed, and comment here, the speed is in miles per hour, and some public methods. We want to set the name to whatever we give it. We'll give it, tell them the horse's name is Mr. Ed. We want to be able to get that out, so we'll just return the name. And we have a virtual, no return, run. So we want to be able to make this horse run. And it's virtual because we know we're going to override this function in derived classes. As I mentioned earlier, and I will mention again, when you design your classes, design them to be derived or not to be derived. It's not a good idea to try to derive from classes that have not been derived, that have not been designed to be derived. So in this case, we designed it to be derived, so we know that the speed is something that is protected and is going to be in common with all the derived classes, but the name is something that belongs to the horse class by itself. But you can get the data in and out by calling the public methods. And our run method here says we're going to set the speed to 30, which is the protected class, and we're going to print out we're running. So the horse is running, is going 30 miles per hour, and we print out we are now running. Now here's a class, racehorse, which inherits from the public section of the horse class. And this is your syntax here. You have class, the name of the class, your colon, the public keyword, and then the name of the class you're inheriting from. And we're not going to add any additional attributes, but we're going to override the run method. So instead of going 30 miles an hour, we're going to set it to 35 miles an hour. And then we're going to say, we're running fast. I actually looked up for this assignment, the fastest racehorse, the record is like 43 point something miles per hour. So I think 35 is reasonably fast because we don't have the fastest racehorses in this program, but it's reasonably enough fast. Now we also have a trotter and another subclass. And there's our colon. It's public horse. So a trotter is a racehorse is not allowed to gallop. So you have the horse there. I'm sure you've seen this. You have the horse. He's got the little carriage behind it. The jockey is not sitting on the horse. He's in the carriage behind him. And he's trying to urge the horse on. And the horse trots as fast as he can without galloping. So he can't go quite as fast as a galloping horse. They go pretty fast. So in this case, we have the run class where we override it and set the speed to 0 and say you're not allowed to run. If the trotter starts running, he's breaking the rules. And we'll add an additional method called trot, which sets the speed to 25 and prints out that we're trotting. So here we have a real quick inheritance tree. We've got the horse, we have a racehorse, and we have the trotter. So beyond this, now we can start writing some code that takes care of whatever the horses are supposed to be doing in this particular application. Now, one of the things about C++ that's unique compared to some other popular languages, you are allowed to have multiple inheritance. So you can inherit from this and from that. You can have a racehorse that inherits from the horse class and inherits from the aircraft class, so that this horse will go really fast. You have to be careful with your design, of course. So here we have an example. I think it's a little bit better example. We have a vehicle, which describes the attributes of vehicles, of course. And then we have something in Java, you would call this an interface. It's licensable, but it actually, unlike an interface in Java, this particular object would actually have some data in it and some methods in it that would describe what being licensable means. And what that means is you have to pay a tax or a fee to your local government that says, I am now licensed to operate this, whatever it is that's licensable. So it requires some legal registration, fees, taxes, etc. Now, an automobile is a vehicle, and it is licensable. You have to pay the state some money. You have to pay them every year, and they'll give you a little sticker that you place on your license plate, and your license plate identifies that particular vehicle. So you can have all sorts of descriptions about your automobile, such as the make, the model, what its miles per gallon is, whatever else it is. And the licensable would have data such as your license number, what your fees are, how much did you pay for this particular license. Now you have an off-road vehicle, an off-road bike, a two-wheel motorcycle with big, huge, knobby tires. People drive them around in dirt and they wear their helmets and they die all the time because those things are dangerous. But you don't need a license for that because you're driving it off of the public roads. So an off-road bike is a vehicle, but it's not a licensable item. Whereas a hunting rifle can be, I should say, we could have a whole other tree here that's not mentioned. A hunting rifle is a weapon, or a hunting rifle is a rifle, and it is licensable. You can go down and get a hunting license that gives you the right to take that hunting rifle out into the woods and hunt deer or elk or whatever you're going to. But it's not a vehicle. So you can have some very complex relationships using multiple inheritance. It's something to be very careful of, that you make your design very tight and try not to create conflicting relationships. So watch out for overlapping names for functionalities. If you have a drive method in automobile and a drive method in licensable, which is unlikely but possible, and you want to instantiate an automobile, which has now got methods from automobile, has got methods from licensable, and you say, I want to drive, the compiler will say, well, which drive do I use? I use the automobile drive or the licensable drive, and there's ways around that. You're much better if you don't have any of these overlapping names. You're much better if you don't have overlapping functionalities. One of the nice things I like about this example, there's almost nothing in common between an automobile and licensable. It's a completely different domain, so there should be no functionality that's in common that overlaps between those two to cause any kind of confusion. But anyhow, if you do get name confusion, you can use a namespace operator, which is 2 colons. So what you would do, if you would have a licensable drive, you would say, try to spell it right, licensable, colon, and then the name of whatever method is in common. So we do want to avoid functionality and overlap when you make these design decisions. Also be careful of the diamond problem. If you have something, probably one of the more famous examples is the duck-billed platypus. Well, what is a duck-billed platypus? Well, it's kind of a bird because it's got the beak and it lays eggs. It's kind of a mammal because it's got fur and it has other things that mammals have. But so let's put that out here. We've got the duck-billed platypus. I'm going to put DP and say that is a bird and it is a mammal. Now, as it just so happens, a bird is a animal and a mammal is a animal. So if you want to call a method from the animal class, you've got a confusion. Do we use the bird one? Because bird might have overridden that, such as run has been overridden with fly, or fly does something else. Mammal here is a give birth, or where bird says lay eggs, that sort of thing. So you run into confusion between these diamonds. And again, you can use the namespace operator to help you resolve your conflicts. But you're better off if you can make your design to avoid this type of situation in the first place. It makes your code much easier to read, much easier to maintain. So you can confuse humans and the computer, so you're better to avoid it if you can. So here's an example of multiple inheritance. We have a vehicle. It's got some protected items, its speed, its X position, its Y position. As I mentioned earlier, we've got the class licensable. Its protected items are its tax number, whatever its number is, license plate number, vehicle ID, what have you, the fees that are required, the tax rate based, the percentage of the purchase, what have you. And then you've got an automobile. You're defining the class automobile. There's your colon operator. This is, I want it to be a public vehicle, then comma, and then public licensable. So now automobile has just been multiply derived from two superclasses. And we're adding, for the automobile, something that's not in the vehicle, something that's not in licensable, the model, where there's Ford, Toyota, etc., the make, where there's a Ford Focus, a Toyota Camry, etc. And we will have the ID for an automobile is called the vehicle identification number, or VIN for short. So specifically for the automobile class, we're going to have set VIN. So we give it the VIN, and we grab the licensable tax number and set that equal to the automobile VIN. So there's our multiple inheritance. Now we need to talk a little bit about constructing your objects. When you declare a new object or a new group of objects, a vector of objects, an array of objects, the object has to allocate memory. So C++ objects have a constructor that allocates the required memory to hold an instance of the object, all of its private data, all of its protected data, all of its public data. You don't need to hold the functions, of course, because the function's in the class definition. But all the data builds up that object that makes that an object versus unique from some other object. Now your default constructor, if you don't provide any constructor at all, the compiler will give you a default constructor. Whenever you just declare an object, like we had horse H1, that will call the default constructor. And if there aren't any other constructors, the compiler will create one for you. It's generally not a good idea to let the compiler do that. You can if you know what you're doing, but generally you just put a default constructor in there, and that would just be for horse. You would just say horse, no parameters, and you don't have to do anything. Just have empty braces. It's not doing anything. The compiler will allocate the memory and everything else. But you probably want to set. It's good practice to define your own default constructor that initializes your attributes to something that's a safe value. So like its age, let's say it's equal to 0 perhaps. Weight. Now, these may or may not be safe values, but whatever those particular attributes are, you define, well, we have a brand new horse that's constructed out of the heap memory. We want to make sure that all of its data has got legal value, safe values. Its age and weight should not be negative. Make sure they're not negative. Set them to 0. Now, we also have a copy constructor. The compiler will create a copy constructor if you don't provide one. And it does what's known as a shallow copy, which we'll talk about in a little bit. And so you may need a deep copy. If you need a deep copy, you need to write your own copy constructor. Now, the other constructors we'll talk about overload. So you need to provide some parameters, for example. So let's overload the default constructor with something that sets the age. Let's provide an A as a parameter. So instead of setting age to 0, we'll set age equal to the parameter that was passed in. Because we wanted to define a new horse, we want the age to be 3 years old, for example. So when we call horse up here, when we define it, we'll call it age2, and we'll put 3 in here. So instead of calling the default constructor, it will call the overloaded constructor with parameters, specifically the one that sets the age equal to whatever number you give it. So we're going to talk about all that again a little bit more here, a little more detail. So your default constructor. The compiler will create one. If you didn't give it a constructor, the compiler has to give you a constructor. Otherwise, you can't construct a new instance of your variable. So it will give you something that doesn't do much except that it'll give you enough memory for all of the members. So it does nothing but allows you to declare something. Here's an example. We'll have a horse. It's got a name. It's got a speed. We'll define a default constructor. So whenever we make a brand new horse, we have to do a constructor. What we're going to do is set the name equal to unnamed horse. And we're going to set the speed to 0 because it's a brand new horse, was just constructed. He's sitting there at rest. He has no name, and he's sitting at rest. He's probably wondering, what's my name? Well, you'll have to give it a name later. So here's an example. We're constructing an instance, one horse. It will have unnamed horse as its name, and its speed will be 0. Here we have a vector of 20 horses. So if you remember from our template classes, we have the vector object that's been defined to be a horse. This is our vector container, which is using the template design. So we have a horse, and we're going to call the object racers, and we're going to initialize it to having 20 objects. So we will actually call the horse constructor 20 times for each of the 20 instances of horse that are in racers. So if you were to output one, say racers at 5, and what's your name, horse, at 5? You say, I'm an unnamed horse. How fast are you going, horse, racer at 5? Says, I'm not going anywhere. My speed is 0. And we have shallow copy. If you don't provide a copy constructor and you copy one object instance into another object instance, the compiler will do a shallow copy, which sometimes is fine. That's all you need. So the compiler does that automatically. It does that for you. Each member of the object is copied to the new object. So here's an example. I can't think of a real nice example, so I just call this stuff. It has two members, int and int, float, a float. So here's our public constructor. We're going to define the two parameters. So we're going to have a and f, which is int and the float, and we're defining it this way. So the integer will become the value in a, the f will be going to a float, and we'll also have a method here that just prints out the data members. So we'll pass it an O stream, which is the output stream that we're going to output to. And this is already wrong. This should be O. Let's erase all this, fix this. Oh, there we are. Because we have O as the input parameter, as the output stream that we want to output to. So we're going to output to that output stream an int, the value of the integer member, a colon, and then a float, the value of the float member. So here is a definition. We're declaring a new instance of stuff called A. The integer will be set to 10, the float will be set to 15.5. And here's our copy. We're defining another object called stuff named B, which is going to be set equal to A. So A data is going to be copied to B. And I already made another mistake here. Let's fix that real quick. So I probably should have just left that all together, but I didn't, so let's make it right. Let's see here. Let's put a semicolon here. Hang on a second. I have to redo this whole class now. Right, it doesn't erase well, so let's get rid of it like this. So we'll print out A. What we'll do after we print out A is we'll call the A print method and pass it C out as the parameter. And then we'll C out B and then do the same thing with B and call its print and pass it C out as the output stream to send the data to. So what will happen is, I'll figure out what this will happen without me telling you, but I'm going to tell you anyway. This will print out 10:15.5. After doing the shallow copy, each one of these members was just copied over to the other member, to the other object. So we do print, it should print out the exact same thing. So we'll see A colon, and then 10:15.5, B colon, and 10:15.5. That's your shallow copy. That's what you get if you don't provide a copy constructor. The compiler will give you one. This may not be good. Let's take a look at a deep copy. What happens if you need a deep copy, but you don't get one? So here's where you might need a deep copy. Let's say we have a character pointer to a name, and one of the rules we're going to have for this particular object, this employee object, is we're not going to allow it to be null. So every time we construct a new employee object, we want to make sure that name pointer is pointing to some valid memory. So the way we're going to do that is to use a strdup function and pass it an empty string. Now what strdup does, if you don't recall from strings, is it will allocate enough new memory to hold the string that is given as a parameter. So it'll give new memory and it returns a pointer to it. So name is now pointing to this empty string. It's not this particular empty string. It will allocate new memory and then put nothing in it. Now our destructor, since we've allocated new memory to hold the name that we're pointing to, our destructor needs to free that memory. Otherwise we'll have memory leaks. We don't want memory leaks. A memory leak is where you allocate memory and then you don't use it anymore. You allocate memory, you don't use it anymore, and eventually you run out of memory and your system will crash. So when you don't need memory anymore, give it back to the system. So which is what we're doing right here. Here's a method. We're going to set the name. Now, in setting the name to something, what we're going to do, since our rule is it always points to something, that means name has got some memory associated with it. So we want to free it first, and then use strdup again to take the parameter, which will be pointing to some other memory, and allocate some fresh memory, put that string into that, and then point name to it. And of course, our getter just says, just return the value that's in there. So there's our employee. Now here we have an instantiation, A1. We're going to set that name to Alvin. So when we run this, our constructor is created, which sets the name to an empty string. So at this point, the name is pointing to empty string. Now we call the set name function. So the pointer to the empty string is freed, and then some memory for Alvin is allocated somewhere, and we set name pointing to that. Now we have in our expression, let's say this expression is 10 is greater than 5. That way it will be true. We'll go into this particular function, and we're just going to define a new instance of employee called B1, and we want it to be a copy of A1. The shallow copy, since we didn't provide a copy constructor, it will copy this pointer name into B1. Now the problem with that is this name, Alvin, is in some memory someplace. Let's put it right here. And A1 name is pointing to it. Now when I do this with the shallow copy, now B1 name is pointing to the same memory, because all I copied over was the pointer. Now, when this goes out of scope, everything that was declared inside that block, when you exit the block, everything inside is destroyed. It gets put back on the heap. So B1 is destroyed, which says, okay, free this memory. So it takes this memory and puts it back to the heap, and gives it back to the system. Except the problem being A1 is still pointing to it. And that's where you run into a problem. So it depends on how your compiler is set up. Nothing might happen, except the next time you try to access it, it's pointing to some invalid memory. You could crash here. When I tested this, it crashed when it left scope. So my particular compiler's got some type of testing in there that said, okay, this pointer is good, this pointer is good. And when I did this, the pointer became bad. And it knew that as soon as it left scope. So I got a runtime error when I tested this. So the object A1 is invalidated by the object B1 being destroyed, because they both had a shallow copy pointer to the same memory. So what we need to do is create a deep copy. Now, the reason why it's called deep copy, because you may have all sorts of members that are other objects. Those objects could have, their members are other objects. And at any one point in there, there could be a pointer to some new memory, either a pointer to a character string, or it's got to allocate an array of what other objects, and it has to pull them in off the heap, and it has to initialize them all up. And when you do a copy of this object to that object, you want to go through each one of the members, and the member members, and the member members, and copy all of that data over without invalidating any pointers. So here we have the same employee class, we have the same constructor, but now we have an additional copy constructor. So what we're going to do is provide a parameter of the type of object that's being copied, which is employee. We're going to use the reference, and we're going to promise not to change it. So what we're going to do, now see, this is wrong, because I should have free, because, oh no, that's not right, that's wrong, it's right. Because this is a constructor. This did not exist before. Since it did not exist before, name it doesn't point to anything. But it points to something now. It points to brand new memory to hold the name of the object being copied. So now, when I have over here Alvin, I have A1 name is pointing in the memory someplace where it says Alvin. And I use the copy constructor this way to define my new object B. So B1 name is also pointing into memory, but now it's different memory, because I created a brand new pointer to point to some brand new memory and copied that data over into the new memory. So now when it goes out of scope, B1 is destroyed. It calls the destructor, which frees its version of the string. And I go back, and now I can print out the get name for A1, it prints out Alvin, everything's good, everything's happy. So if you have a deep copy issue with your classes and objects, you make sure you write a copy constructor. Is this a good design, or is it just multiple inheritance? What do you call that? A race, or oh, that's a Mustang. That's what that is. Anyhow, that's it for today's lesson on object-oriented. Next lesson we'll cover some more object-oriented materials. But thank you for visiting educator.com.